Alright, so let's take a minute here to talk about harmonics and standing waves in some instruments. Harmonics instruments, get it? Okay, so I pulled up this little picture here that's got a couple different standing waves. It's got all three situations that we've discussed briefly in class yesterday. We've got a column that is open on both ends, a column that is open on one end, and a stringed or closed on both ends, which basically gives the same, or they're basically the same things. So we'll start with a string, right? If this is our guitar string, and if we were to pluck it once, it would vibrate up and down. It would give us a standing wave right here. This is what we call the fundamental frequency. We can then create harmonics by creating nodes along this line. For instance, if this is the fundamental frequency right here, this setup that we have in this illustration is going to be the first, second, the third harmonic of this string that has this fundamental frequency. This would be the 1, 2, 3, 4, fifth harmonic for that frequency. And so I think the strings is probably the easiest to grasp. But if we go over here to the open column and the closed on one end column, it gets a little bit trickier. So what we've got, and let me just zoom out here just a little bit to include these equations that I'm now going to start to use. This equation right here, and let me grab a pencil. This equation goes with the open on one end, closed on the other, whereas this other equation right here belongs with open on both ends. And so let's start with closed on one end. This is what we call the fundamental frequency right here. The fundamental frequency is also referred to as the first harmonic. So this is the fundamental, and that's all right, and it is also the first harmonic, just as this is the fundamental frequency or the first harmonic. It's the tendency of that object. This object, if it's closed on one end, it has a tendency to go right to this frequency. If you blow over the top, this is the frequency that you're going to get out. If you pluck this string without any barriers or anything, not pushing on any frets or anything, this is the fundamental frequency of that string. This is the fundamental frequency of, or the first harmonic of, a column that is open on both ends. Okay, so now if this is the fundamental frequency, the second, or the first harmonic, the second harmonic would be this next quarter of a wavelength, which is right here, but that doesn't occur on a column that's open at one end, because where the column is open, you've got to have your antinodes, and so the second frequency, if there were one, would be right here at this point. However, this doesn't occur because we have an open end. So we don't have a second harmonic on a column that is closed at one end. We have the first harmonic, which would be right about here. The second doesn't exist, and we have the third harmonic, which would show up here. So that's a little bit on closed at one end, open at the other, and you can use these equations right here to solve for the wavelength of each of these. L is going to be the total length of the column, and N is going to be the harmonic that you want. So for the first harmonic, if we plugged a 1 in here and we knew the length of this column, we could tell the wavelength is going to be this 4 up here. It means the wavelength is going to be 1/4, which makes sense. This is 1/4 of a wave from here to here. Second fourth, third fourth, fourth fourth, to make an entire wave if it were to sketch out across the page. So this is 1/4 of a wave, and that's where we get this lambda, which is wavelength, is 4L over N. The only thing to remember is that you only have the odd, and I should write that in red if I can get to my red color here. You only have odd harmonics when it's closed, and the way that I remember that is one end is closed, so we have 1, which is an odd number. You only have the odd number harmonics for these guys. Okie dokie. So let's move to a column that is open on both ends. And when we look at that column that's open on both ends, we can see this is our fundamental, or our first harmonic. And I'm all off on colors, but we'll just jump back into it. Here's our first harmonic, fundamental frequency. It's got to have an antinode at both ends. So this is our first harmonic. You may notice that this is a half of a wavelength. So whereas before it was a 4L over N, now for the open at both ends we have 2L over N, meaning that the fundamental frequency is a half a wavelength. Now this guy, this one right here, for our second harmonic would be from here to here. Or excuse me, this is our first harmonic. And so this is going to be our second harmonic right here. And so the second harmonic does occur in the open at both ends tube, whereas it did not occur at in the previous discussion. So this would be our first, second harmonic right here, and this is going to be our first, second, third harmonic, and we can put little dashes here. So here's the first, this is the second, this is the third. So this is our third harmonic for a pipe that's open at both ends. Again, you can use this equation right here to calculate the wavelength that would be required. If we know the length of this column and we know which frequency we can get, or which harmonic we want, we can then calculate what the wavelength would be of that harmonic. Given the wavelength, given the speed of sound in air, which is somewhere between 330 and 340 meters per second, we can then calculate the frequency, which will tell us the pitch. Remember from our little demonstration in class on Tuesday that the shorter wavelength, lambda, gives us a large frequency, and the converse of that is also true. If we have a long wavelength, we get a small frequency. So short wavelength, high frequency, high pitch. Long wavelength, low frequency, low pitch. And so that's how you get your sounds of your different instruments and so forth. It's all just standing waves and harmonics. Hopefully that clears a little bit of this up, and we'll see you in the next session.